Hello everyone. The topic is on magnetic field due to solenoid. The most important derivation in Ampere's law is finding magnetic field inside a solenoid. What is a solenoid? Solenoid is a long coil of wire closely wound in the form of helix, as shown in this diagram. The wire is coated with an insulating material so that when the adjacent turns physically touch each other, they are electrically insulated. We know that when electric current is passed through the solenoid, the magnetic field is produced. The magnetic field of the solenoid is given by the superposition of magnetic fields of each turn of the solenoid. The direction of magnetic field due to solenoid is given by right-hand palm rule. Inside the solenoid, the magnetic field is uniform and parallel to its axis, whereas outside the solenoid, the magnetic field is negligibly small. Based on the direction of current, one end of the solenoid behaves like North Pole and the other end behaves like South Pole. If the current carrying solenoid is held in right hand and if the fingers curl in the direction of current, then the extended thumb gives the direction of magnetic field of current carrying solenoid as shown here. Hence, magnetic field of a solenoid looks like the magnetic field of a bar magnet. Here we consider a circularly wound coil. Generally, the length of the solenoid is large as compared to the transverse dimension. For example, if the solenoid has circular turns, the length is large as compared to its radius. If it has circular turns, the length should be large as compared to the edges. The magnetic field due to a current carrying solenoid can be easily pictured by examining the field due to a circular current. The field lines due to a circular current is shown in figure 1. The diagram A shows the magnetic field lines due to a circular loop A carrying a current and also due to a similar loop B placed coaxially and carrying equal current. We know that at point P, which is quite off the axis, the magnetic fields due to the two loops are in opposite directions. On the other hand, at point Q, which is on the axis or close to the axis, the two fields are in the same direction. Figure P shows the resultant field lines due to the due to two loops. A solenoid may be thought of as a stack of such circular currents placed coaxially one after the other. Diagram C represents the field due to loosely wound solenoid. The fields at an outside point due to the neighboring loops oppose each other, whereas at an inside point the fields are in the same direction. These tendencies to have zero field outside and a uniform field inside became more and more effective as the solenoid is more and more tightly wound. The magnetic field inside a very tightly wound long solenoid is uniform everywhere and is zero outside as is shown in figure D. So the next slide is about to calculate the formula for the magnetic field due to solenoid. Consider a solenoid of length L having N turns. The diameter of the solenoid is assumed to be much smaller when compared to its length and the coil is wound very closely. To calculate the magnetic field at any point inside the solenoid, we apply Ampere's circuital law. As Ampere's law states that the line integral of magnetic field over a closed loop is mu naught times the net current enclosed by the loop. It is given by the equation. The line integral B vector dot dl vector is equal to mu naught times I enclosed, where I enclosed is the net current linked by the closed loop C. Note that the line integral does not depend on the shape of the path or the position of the conductor with the magnetic field, where mu naught is the permeability of free space. So, mu naught times total current enclosed by Amperian loop, that is, we consider a Amperian rectangular loop ABCD. Hence, the equation on the left hand side is written as closed the closed integral B vector dot dl vector is equal to line integral a to b vector dot dl vector plus line integral b to c b vector dot dl vector plus line integral c to d b vector dot dl vector plus line integral a to d to a b vector dot dl vector. Here we equate the second and fourth term to be 0 because the length element along BC and BA are perpendicular to the magnetic field which is along the axis of the solenoid. Therefore, the integral b to c b vector dot dl vector is equal to modulus b vector modulus dl vector cos 90 degree. We include cos 90 degree because it is perpendicular. We know that cos 90 degree is 0. Hence, the integral b to c b vector dot dl vector is 0. As the same for integral d to a b vector dot dl vector is equal to 0. Even the third term is equated to 0 as we know that the magnetic field outside the solenoid is 0. Therefore, the integral c to d b vector dot dl vector is equal to 0. The line integral AB is parallel to the solenoid axis and is parallel to the magnetic field inside the solenoid. Thus, the integral A to B vector dot dl vector is equal to B times of the integral to the limit of A to B dl cos 0 degree. We know that cos 0 is 1. Therefore, it can be written as B times integral A to B dl. Adding all dl from A to B is L. Therefore, the equation can be equated to BL. Let N be the number of turns per unit length along the length of the solenoid. A total of NL turns cross the rectangular Amperian loop ABCD. Each turn carries a current I. Therefore, the net current crossing the Amperian rectangular loop ABCD is NLI. On equating the terms on both the sides in Ampere's law, that is, line integral B vector dot dl vector equal to mu naught times NLI. That is, BL is equal to mu naught NLI. L on both the sides gets cancelled. Therefore, the magnetic Therefore, the magnetic field due to a long current carrying solenoid can be written as B is equal to mu naught times Ni. Since N is a constant for a given solenoid and mu naught is also a constant, for a fixed current I, the magnetic field inside the solenoid is also a constant. So the next slide is about the magnetic field due to a solenoid. So the first question is, a long solenoid is wound by winding 20 turns expressed in centimeter inverse. What current is necessary to produce a magnetic field of 20 millitesla inside the solenoid? First, let's write the given terms. So number of turns and magnetic field is given and number of turn is expressed in meter inverse and magnetic field is given as 20 into 10 to the power of minus 3 Tesla. So they have asked us to find the current inside the solenoid. To find the current inside the solenoid, we use the formula of a magnetic field due to a solenoid. That is, B is equal to mu naught Ni. From this, we can write I is equal to B divided by mu naught N. Substituting the values of B, mu naught and N. That is, B is 20 into 10 to the power of minus 3 Tesla divided by 4 pi into 10 to the power of minus 7 Tesla meter ampere inverse into 20 into 10 to the power of 2 meter inverse. On cancelling the terms, we come to know that I is equal to 7.96. On rounding, I is found to be 8 milliampere. Therefore, using the formula magnetic field due to a solenoid, we find the current inside the solenoid to be 8 ampere. So let's get into next question. The question is that find the magnetic field of a very long solenoid consisting of n closely wound turns per unit length on a cylinder of radius r, each carrying a current I. So from this, in the figure 5.34, it is shown there is a long solenoid of n turns of which has a radius r and it carries current I. The point of making the winding so close is that one can then pretend each turn is circular. If this problems you, after all, there is a net current I in the direction of the solenoid's axis, no matter how tight the winding. This pictures instead a sheet of aluminum foil wrapped around the cylinder carrying the equivalent uniform surface current I is equal to Ni expressed in the figure 5.35, or make a double winding going up to one end and then always in the same sense going back down again, thereby eliminating the net longitudinal current, but in truth this is all unnecessary fastidiousness, for the field inside a solenoid is huge and the field of the longitudinal current is at most a tiny refinement. So for this problem, the solution can be written as, first we will be finding the direction of magnetic field. For that we should know about whether the radial component is present or not. Here there is no radial component, and if suppose a Bs were positive, if we reversed the direction of the current, then Bs would be negative. But switching I is physically equivalent to turning the solenoid upside down, and then certainly should not alter the radial field. And there is no circumferential component. And from the figure 5.36, it is known that B pi would be constant around an Amperian loop concentric with the solenoid. Hence, on writing the Ampere circuital law, that is line integral B dot dl is equal to mu naught times I enclosed will be equal to B pi into 2 pi s, which is equated to 0. This shows that the loop encloses no current. Since the magnetic field of an infinite closely wound solenoid runs parallel to the axis, from the right hand rule, we expect that it points upward inside the solenoid and downward outside. Moreover, it certainly approaches zero as we go very far away. With this in mind, let's apply Ampere's law to the two rectangular loops in 5.37. That is, there is two rectangular loops here. So the loop 1, which lies entirely outside the solenoid with its sides at distances A and B from the axis. That is, the Ampere circuital law for the loop 1 can be written as line integral B dot dl will be equal to B times A minus B times B into L will be equal to mu naught times I enclosed equal to 0. That is, BA will be equal to B times of B. Eventually, the field outside does not depend on the distance from the axis, but we agree that it goes to 0 for large S. It must therefore be 0 everywhere. The same result can be even found from Biot-Savart law, but it is difficult. Let's go for loop 2, which is half inside and half outside. So Ampere's law gives line integral B dot dl will be equal to BL is equal to mu naught times I enclosed will be equal to mu naught NIL, where B is the magnetic field inside the solenoid. So the right side of the loop contributes nothing, hence magnetic field will be zero. Therefore, magnetic field can be expressed as mu naught times NIZ cap for inside the solenoid, and B would be equal to zero outside the solenoid. So we have found that the magnetic field inside the solenoid can be expressed through mu naught Niz, and B would be equal to zero when for the in case of outside the solenoid. Notice that the field inside is uniform. It does not depend on the distance from the axis. In this sense, the solenoid is to magnetostatics what the parallel plate capacitor is to electrostatics. A simple device for producing strong uniform fields. So as asked, we have found the magnetic field inside and outside the solenoid. Let's go to the third sum. The question is, find the vector potential of an infinite solenoid with n turns per unit length of radius r and current I. Here we go with the equation line integral A dot dl will be equal to integral curl of A dA is equal to integral B dot dA is equal to pi, where pi is the flux of B through the loop. And on applying Ampere's law, that is Ampere's circuital law, closed integral B dot dl will be equal to mu naught times I enclosed. When B tends to A and mu naught I enclosed tends to pi, if symmetry permits, we can determine A from pi. So the problem is that with a uniform longitudinal magnetic field, mu naught Ni inside the solenoid and no field outside is analogous to the Ampere's law problem of a fat wire carrying a uniformly distributed current. The vector potential is circumferential. Using a circular Amperean loop of radius S inside the solenoid, we get the equation as closed integral A dot dl will be equal to A times 2 pi s will be equal to integral B dot dA will be equal to mu naught Ni into pi s square, where from this we can write that A will be equal to mu naught Ni divided by 2 into S pi cap for S lesser than equal to R. For an Amperean loop outside the solenoid, the flux would be integral B dot dA will be equal to mu naught Ni into pi R square. Since the field only extends out to R, thus A is equal to mu naught Ni divided by 2 R square divided by S pi cap. This equation will be suited when S greater than equal to R. So the next question is, an infinite solenoid n turns per unit length of current I is filled with linear material of susceptibility psi m. Find the magnetic field inside the solenoid. For this problem, we can approach like if B is in part due to bound currents, we can't compute it directly. Hence, we go from H from the free current alone using Ampere's law. That is, H can be represented as H is equal to Niz cap. From this, B would be equal to mu naught times 1 plus psi m into Niz cap. If the medium is paramagnetic, the field is slightly enhanced. If it's diamagnetic, the field is somewhat reduced. This reflects the fact that the bound surface current would be KB will be equal to curl of M, that is M cross N cap is equal to um, psi m of h cross n cap will be equal to psi m of n times I pi cap. Is in the same direction as I in the former case, and psi m will be greater than 0 and opposite in the later as psi m less than 0. From this, it's shown that the volume-bound current density in a homogeneous linear material is proportional to free current density. That is, JB will be equal to curl of M is equal to curl of substituting the value of M, that is psi MH will be psi MJF. That is, unless free current actually flows through the material, all bound current will be at the surface.